Welcome back, Night Owls. This is Dr. Nighttime, and tonight we are obsoleting the quadratic formula. Yes, we are making the quadratic formula obsolete. We're introducing something that will remove the need to remember the quadratic formula in those cases when the leading coefficient is 1 and the other coefficients are integers. Otherwise, the operations we'll be doing here will be a little cumbersome. So let's start with the simpler way of solving quadratics, right? Factoring. So consider something of the form x squared plus 8x plus 12 equals 0. We recognize that that factors into x plus 6 times x plus 2 equals 0, right? And typically the way you'll do that is you'll look at the number 12, right, that additive constant at the end. You'll think about what can multiply together to make 12 and try to get a pair that adds to 8. And you realize, okay, 6 and 2. So either x plus 6 is 0 or x plus 2 is 0, because if I have two things multiplied together that get me a 0, one or both of them has to be 0. And we get that x is negative 6 or x is negative 2. Now it turns out there's a systematic way to factor rather than just guessing the possibilities. So let's look at this problem. X squared plus 26x plus 144 equals 0. 144 has lots of factors. We probably don't want to check all possible combinations to see which pair of them multiplies to 26. Fortunately, there's a more systematic way to do this. The key here is to look at the linear term first. That's this middle term, the 26x. Rather than think about what multiplies together to 144, we think about what adds together to make 26. Now, there are lots of possibilities for that, obviously. But what if we wanted to maximize the possible product? So ignoring the 144, what's the greatest product we can get from two numbers that add up to 26? Well, to maximize the product, you split them evenly, right? You go 13 and 13. If two numbers have to add to 26, the maximum possible product is the one you get when you multiply 13 and 13. That gets you a 169. All right, now the product we're looking for is 144, not 169. But let's see what happens when we move our factors apart. We start with them dead even. We get 169. If we move one in either direction, we get a 12 and a 14. That gets us a 168. That is one less than 169. If we move them 2 away from even, 11 and 15, that gets us a 165. That is 4 less than 169. If we move them 3 away, that's a 10 and 16. That's 160. That's 9 less than 169. So we need a product of 144. 144 is 25 less than 169. I'm sure you see the pattern here, that to move over by some amount, your product decreases by the square of that amount. So to aim for 25 less than our maximum possible product, we have to move our 13s over by the square root of 25, or 5. So we say, okay, one of them is going to be 13 plus 5, the other is going to be 13 minus 5. That gets us 18 and 8, and sure enough, 18 and 8 add up to 26 and multiply together to 144. Gets us x plus 18 times x plus 8 equals 0, so x equals negative 18, or x equals negative 8. Now, as we know, if you've ever had to use quadratic formula for something, sometimes you get a nasty square root as part of your answer. Well, it turns out, without remembering the complicated quadratic formula, you can find those nasty square roots without much trouble. Consider this one. X squared plus 10x plus 19 equals 0. To maximize the product of two numbers that add to 10, you split it evenly, 5 and 5, you multiply them together. You get 25. 19 is 6 less than 25. So in order to reduce my product by 6, I have to move over by the square root of 6 in each direction. So I need to say x plus 5 plus square root of 6 and times x plus 5 minus square root of 6 equals 0, right? I did x plus 5 times x plus 5, but then I moved by my a and my b, I moved my factors over by square root of 6 to get x equals negative 5 plus or minus square root of 6. Finally, well, what if you get something that has no real solutions? So suppose you have x squared plus 10x plus 29 equals 0. Now, my maximum possible product is going to be 25. My actual product is 29. It's more than my maximum possibility. So depending on whether they're having you use imaginary or complex numbers here, they'll either have you say the maximum product is, the actual product is greater than the maximum possible product, which would mean that that this doesn't have any real solutions. Or you could say, well, I have to subtract -4, so I move over by the square root of -4, and they'll either tell you that doesn't exist, or it's equal to 2 times the imaginary quantity I, to get x equals -5 plus 2i and x equals -5 minus 2i. It was a bit over a year ago that a friend of mine sent me a text message saying, hey, Dr. Nighttime, you teach math, right? Have you seen this? I looked at this, and I looked at the paper she sent me the link to, and I said, I wish I thought of that. This would have made things so much easier for me back when I was learning quadratic formula if I had just seen this. So, and when I've introduced this to students, they typically have that same, I wish I knew about that earlier reaction. Got to the point where I was showing one of my students, this was about a year ago, shortly before the COVID-19 pandemic, when I could meet with students in person. We were in the local library, and I got so excited showing them this that the librarian had to come over to me and say, "Sir, we appreciate what you're doing, but could you please do it a little more quietly? This is the library." Anyway, if you like the way I explain things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.